Hello there, Mr. Sutton here, bringing you the AB Calculus 412 Extra Practice Number 1 Solutions on Motion. This problem involves a fair amount of reading. We have a file downloaded to a computer at a rate modeled by the differentiable function f of t, where t is time in seconds since the start of download. F of t is measured in megabits per second. That's going to be important. Which of the following is the best interpretation of f prime of 5 equals 2.8? So what we're saying here essentially is that at 5 seconds, the rate of download rate is 2.8 because f is the download rate. It's a rate. It's downloaded at a rate modeled by f of t. So if you're taking f prime, you're doing the rate of downloading. So that's going to mean we have a units then, since f of t has a units of megabits per second, f prime is going to be megabits per second squared. So let's take a look at the different answer choices and see which one matches what we've written here. So choice A, at time 5, the rate at which the file is downloaded is 2.8. Nope, this would be if you did f of 5 equals 2.8. Choice B, at 5 seconds, the rate at which the file is downloaded to the computer is increasing at a rate of 2.8. Well, that makes a little bit more sense because the rate is increasing, so it's a rate of a rate. For choice C, over the time interval 0 to 5 seconds, 2.8 megabits of data were downloaded to the computer. So we didn't talk about how much was actually downloaded. Again, it's the rate of the rate. And then for D, from 0 to 5, the average rate of download was 2.8 megabits per second. So that would be the average value of the f function. And this one, choice C, this would be the integral of the f function, which you may or may not have seen yet in your studies. So then choice B makes the most sense out of this. It's megabits per second per second. For this problem, we have a particle moving on the x-axis with a position given by this x of t function. For what value of t is the velocity of the particle 0? Well, velocity is going to be x prime of t, the rate of change of that position. And that's going to be 2t minus 6 if we take that derivative. We want to know where that equals 0. Well, if you add 6 to the other side and divide by 2, you've got t equals 3, so that's going to be C. For this problem, we have a particle moving on the x-axis for time greater than or equal to 0. Position is given by this cosine of radical t function. We want the velocity of the particle at the first instance the particle's at the origin. So to get the velocity, we're going to need to plug a number into a velocity formula, which, since this is a calculator problem, we can just do Math 8 and use this in our Math 8 at a certain value, but we don't know what time value to plug in yet. To find that, we need to figure out when this particle is at the origin, which means we need to figure out when this x of t function, the x value, the cosine of radical t, equals 0. So we're going to solve this on the calculator. So here I am on my calculator. In y equals, I've entered this function, and I don't really know what window to use to graph this thing, so I am going to just do a window from 0 to, 10. And let's zoom fit this thing and see what happens. And if that doesn't work, I'll do zoom 6. But it looks like I have a pretty clear picture of what's going on. This function's probably going to turn around somewhere and come back. It is, after all, a cosine function when you get down to it. However, the first instance where this thing is at the origin, that's where this function is crossing the x-axis, taking on a value of 0. That's right here. So let me second trace that and calculate that 0. That's between 2 and 3. Press enter one more time. We have a value of 2.4674. So I'm going to quit out of that, and I'm going to store that as alpha A, just so I can bring back that value as soon as I want, as many times as I want. There we go. All right, what do I need to do next? So I've found out that the time I'm looking for is this 2.4 change number. So I'm going to plug that now into the derivative of x prime of 2.4674. And to do that on my calculator, going back here, I'm going to go to Math 8, and that brings up my d over d kind of derivative function. I'm going to use x down there. I'm going to use y1, so I'll do alpha trace and pull up the y1 from the y1 menu here. And for my value, well, I've stored this as a. But actually, come to think of it, I can just reach up here and grab the input that way as well by up arrowing that. So that'll come out to negative 0.318 and some change there. So that'll be answer choice C. On this problem, we have a particle going on a straight line with a velocity given by this v of t function. We want to know the acceleration of the particle at time 4. Well, if you already have the velocity function, the acceleration is just the derivative of that at time 4. So on our calculator, we're going to be doing v prime of 4. Specifically, on my calculator, I went to math and then 8, and then pulled up this d over dx business. So I always differentiate with respect to x. Here's the function, here's the velocity function they gave us. Here's the time they want it evaluated at. Just press enter, and this will give us our acceleration of 1.265. So that's going to be choice C. For this problem, we have a particle going on the x-axis, so we have a velocity function of this in terms of time. We want the acceleration of our particle at time 4. Well, if this is the velocity, the acceleration at 4 is just going to be v prime of 4. So let's just do that on the calculator. So on my calculator, I'm going to go to math, and then option 8, if you scroll down, is this derivative function. I've got x, I've got 3 plus 4.1 cosine of 0.9x, and close that parentheses. And then down here, we want to evaluate it at 4. Press enter. That's 1.633 if I round off. Choice C. For this problem, we have a particle going on the x-axis with a velocity given by v of t equals t squared ln of t plus 2. Based off of that, we want the acceleration of the particle at time 6. So we're essentially just asking for v prime of 6 because acceleration is the derivative of velocity. So let's just plug that in the calculator. So on my calculator, I went to math 8 to pull up this derivative format, and then I did x down there, and I've got my function in here. And just one more thing I'm going to do after the delimiter bar, I'm going to do x equals 6. Press enter. 29.453, which is going to give us choice C. On this problem, the velocity in meters per second of a certain type of wave is given by this 3-radical h function, where h is the depth of the water through which the wave is moving. So basically, the wave speed changes depending on how deep you are in the water. So we want the rate of change in meters per second per meter of the velocity of the wave with respect to the depth of the water when the depth is 2 meters. So we're asking for rate of change of velocity when you get down to it. So we're asking for the derivative of this velocity function when h equals 2. Okay, well, let's find v prime of h in general. This is really just h to the 1/2 power. So that's going to be 3/2 times h to the negative 1/2, just using our power rule. And if you look at the answer formats, none of them have these fractional negative exponents, so I'm going to neaten this up a little bit. This is really 3 over 2 times the square root of h. So now if I want to do v prime of 2, that's just going to be 3 over 2 times radical 2. And that's one of the answer choices, choice C. For this problem, we want to know the maximum acceleration attained on the interval 0 to 3 by a particle with a velocity given by this v of t function down here. So if I want maximum acceleration, if I'm trying to maximize something over a closed interval, then the candidate's test is going to be my best bet. So I'm going to have to find the acceleration function and plug in the endpoints 0 and 3 along with any critical values for acceleration. So let's start by getting that acceleration function. Acceleration, we know, is the derivative of velocity, so v prime, which will be 3t squared minus 6t plus 12 if we use our power rule. And I'm going to have to go one more derivative now because I want the critical values of acceleration to test out in this function along with the endpoints. So that's going to be a prime gives me 6t minus 6. So for finding critical values, I want to know where this equals 0. And that's going to be at, let's see, if I add 6 and divide by 6, that's at t equals 1. So I've got 3 things to test out in the acceleration function that I created up here. I've got 0, 1, and 3. So let's go to it. we've got a of 0 is just going to be, let's see, 3 0 squared minus 6 times 0 plus 12. That's just 12. Zeroes out everything that has a t in it. So that was an easy one. Now a of 1, and this was a no calculator question, a of 1, that's almost as easy. That's just 3 minus 6 plus 12, so that's 9. And now a of 3 is going to be a little bit tougher. That's going to be, let's see, 27 minus 18, which is 9, plus 12 is 21. So out of all of those, 21 is the maximum value, so choice D. For this problem, we have a particle going on a straight line, and the graph of the particle's velocity at time t is shown here. And these j, k, l, and m's, those are constants. So we have our graph intersecting the vertical axis at 0, k, and m. And we have horizontal tangents at, let's see, j and l. Great, this is nice to know. For what values of t is the speed of the particle decreasing? So speed, you have to remember, is the absolute value of velocity. So if you're asking where the absolute value of velocity is decreasing, you're essentially asking where is the velocity getting closer to 0, because the lowest the absolute value can ever be is 0. So if you look at intervals where we're getting closer to 0, well, we're getting further away from 0 here, but now we start going closer from j to k. And then from k to l we get further away, but then we get closer to 0 from l to m. So just using that absolute value kind of definition, it looks like jk and lm are the intervals that we want. Another way of thinking about it, a little bit more methodical way, is your speed is decreasing where your velocity and acceleration have opposite signs. So you could make a little sign analysis chart based off of this graph. So here's velocity, here's acceleration. Velocity is just the function's value. So velocity in this first interval is positive because you're above the x-axis. Acceleration is going to be whether you're increasing or decreasing. Since we're increasing velocity, we have positive acceleration. Next interval, that's going to be positive velocity. And since we're going down now, that's negative acceleration. Next interval, we have negative velocity because we're below the x-axis. And since we're still decreasing, we have negative acceleration. From L to M, we have still negative velocity, but now we're going up, we're increasing, so that's positive acceleration. So looking at where we have opposite signs, this confirms what we saw earlier, that the intervals we want are j comma k and l comma m. So that's going to be answer choice, let's see here, looks like C, j to k and l to m in old school inequality notation. For this problem, we have a particle moving along the y-axis with a velocity given by this function, t times sine of t squared. In which direction, up or down, is the particle moving at time 1.5? So to figure this out, we're going to plug 1.5 into this velocity function that they just gave us, and we'll do that on the calculator in a sec. And the sign of the velocity will tell us whether our particle is going up or down. So let's do that now. So I'm going to y equals, and I'm going to put this in as x sine of x squared. I could just plug things in directly, but I have a hunch I'm going to have to use this velocity function down the road at some point. So let me just put it right in there. So now let me exit out of there, and I'm going to do alpha trace and pull up y1 from my y equals menu. And now I am just plugging in 1.5, nothing else, giving me 1.167. So that is a positive number. That's greater than 0. Since the velocity is positive, that means that this particle, which only has a choice between going up or down, has to go in the positive direction, which means that it's going up. For this part of the problem, they want us to find the acceleration of the particle at 1.5. Is the velocity of the particle increasing at 1.5? Why or why not? So for acceleration at 1.5, since acceleration is the derivative of velocity, a of 1.5 is really just v prime of 1.5, which, since this is a calculator question, we are allowed to just enter directly on our calculator. Now, it's tempting to actually figure out the formula for v prime, but we don't have to. You are allowed to just take the derivative of a function that they've given you at a single point without showing any other work. So let's go ahead and do that. So here's what I'm entering in my calculator. I did math 8 to get my derivative format. I always do dx down there. And I stored the velocity function here in y1, and I'm evaluating this at x equals 1.5, giving me a value of negative 2.049. And they didn't give us any units, so we're not going to give them any units back. Now, the other part of the question, is the velocity of the particle increasing? Well, this is a negative acceleration that we have here. Since the acceleration, which is the rate of change of velocity, is negative, that means velocity is not increasing. It's actually decreasing, not increasing, because of this negative acceleration there. For this problem, we have a particle going along the y-axis with a velocity given by this crazy arcsine, or arctan rather, kind of function. And at time 0, we're told the particle's at y equals negative 1. We actually don't need that for this part of the problem, but if you get to the parts where there's integrals involved, that'll be important then. So for part A, we want the acceleration of the particle at time 2. Well, the acceleration at time 2 is just going to be the derivative of the velocity at time 2. So we can say that A of 2 is really just V prime of 2, which we are now going to find on the calculator. So the first thing I'm going to do here, I'm actually going to enter this velocity function in my y equals. I generally always do this on the calculator parts of an AP exam, so then I can just use y1 instead of retyping this over and over again. So quitting out of there now, I'm going to do math 8 and get my derivative format. I'm differentiating with respect to x, at least as far as my calculator is concerned. And I'm going to do alpha trace and pull up y1 to put in there as my function. And now for the x value, or the t value in this case, that's going to be 2. We wanted v prime of 2, which comes out to negative 0.133. And they didn't give us any units on this problem, so we don't have to worry about giving them any units back. For this part of the problem, they want to know if the speed of the particle described up here is increasing or decreasing at time 2. So with speed, we have to compare the signs of velocity and acceleration at time 2. We already found acceleration at time 2. If we look back at part A of this problem, we found that the acceleration, or v prime, was a negative number, and that's all we really care about for this. So now we're going to plug 2 directly into this velocity function to find the velocity itself, and we'll do that on the calculator. Now the good news is I already entered this as y1 on my calculator, so on my calculator, I'm just going to do alpha trace, pull up y1, and then I'm just going to plug 2 directly into that, which will give me a value of negative 0.436. Well, I'll take their word for it. So since my velocity is negative and my acceleration is negative, since their signs are the same, since velocity and acceleration have the same sign at t equals 2, the particle speed is increasing at that time. If they agree, we're increasing the speed. If they had had opposite signs, then we would have said the speed was decreasing. For this problem, we have a train running back and forth on an east-west section of a railroad track. It's kind of like the particle moving on the x-axis. The velocity of this train in meters per minute is given by some differentiable function v of a, time measured in minutes, and selected values of this velocity function are given in this table here. So this is a table of velocity as a function of time. So based off of this, we want to find the average acceleration of train A over the interval from 2 to 8. Well, finding the average acceleration, you're essentially asking for the average rate of change for velocity, because acceleration is the rate of change of velocity. So this is just an AROC question in disguise here. So we're going to find the average rate of change between 2 and 8 using this table, which means we need to do v sub a of 8 minus v sub a of 2 over 8 minus 2. So then we've got negative 120 minus 100 over 8 minus 2, or over 6, either of those. And if you put units on here, you're actually done with the problem. You didn't have to simplify this. But what are our units going to be? So if we're asking the rate at which velocity is changing, that's going to be meters per minute, or meters per minute squared. And then if you did want to simplify this, well, this is, let's see, negative 220 over 6, which we can reduce to negative 110 over 3. And again, that's going to be meters per minute squared. For this part of the problem, we're asking if the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t between 5 and 8, and then give reasons for our answer. So intuitively, we see that the velocity between these times changes from positive 40 to negative 120. So are we guaranteed that the velocity has to go through negative 100 to get from 40 to negative 120? Well, negative 100 is between these, but are we guaranteed that this is a continuous function, which would allow us to use our intermediate value theorem to prove this? We actually are guaranteed this. Reading the question again, they said that v sub a is a differentiable function. Differentiable implies that it's also continuous. So writing this up now, yes, since the function is differentiable, it is continuous, so the IVT applies. Since negative 100 is between 40 and negative 120, there is guaranteed to be some time between 5 and 8 minutes at which our velocity is negative 100 meters per minute.